Good morning. So your final, I think the midterm, the score midterm has been the TA is done, finished the grading. So you will see you will be able to see your the final answer sheet and everything in the last hour of today. So starting from 11:13, the TA will be here for if you need anything, if you'd like to discuss the grading or anything. This is your final chance, the only and final chance. Okay, so 就今天呢最后一个小时，助教会让大家看分数，所以你要分，或者是你觉得助教扣的太狠了，你就只有这一次机会啊。今天过了就没了。Okay, so the last today we're going to talk about a very important neural network structure we call convolutional neural network. Okay, so. And how about the Kaggle? How you guys doing with the Kaggle? 大家都完成 Kaggle 的测验了吗？ You done with Kaggle? Okay. So the project of the Kaggle is based on real data. So it's the real data from I think it's from a fitness center. 那是一个真的 data， 那不是随便捏造出来的 data， 所以你会发现其实 it's quite noisy. It's something went wrong, and some data, some feature is not independent, like the BMI with height and weight, right? So some of that is correlated. So you need to figure it out what happened with the data. That's if you like to increase your performance or try to avoid overfitting. Okay, so today we're going to talk about the convolutional neural network today. And I think we'll have a very quick introduction of CNNs and finish by I think finish by some advanced structure. I think we'll go to ResonNet, and next week we're talking about generative models. Okay, so let's get started. So historically, I think CNN is the most powerful and most useful way in the first beginning. So it's all about it's starting from a guy that this one just received the Nobel Prize in Physics. We call Hinton, Gregory Hinton. The reason Hinton received Nobel Prize in Physics is not about the propagation, it's not about deep learning, it's about his application using Boltzmann distribution. It's a known thermodynamic distribution in physics. He applied this chaotic stochastic process in neural network. So that's the reason he received the neural. But in this year, last year, I think, in this year, I think 2025, chemistry goes to AI and physics also goes to AI, which means make a mapping of the new world. We're moving to the AI and new algorithm. Okay, so it's starting from Hinton. There was always a competition we call image recognition, image competition for recognize different kinds of images using different, I think, several algorithms. And in 2014, Hinton and his student is the first one used GPU. The first one used GPU and CUDA. And using CUDA, NVIDIA's tech. And they won the prize. They won first prize. So since starting in 2014, everyone just recognized, okay, now we can use GPU for AI and for like a distributed computing in neural network. Then 2016, the first generation of GAN. The GAN is generative adversarial network, is image generation. And it's made by Goodfellow. So if you pay attention to the reference, the textbook I provide, so There's only one reference I listed there is the deep learning. The book name, the name of the textbook is Deep Learning. It's written by Goodfellow Hinton. Okay, so if you're interested, you can take a look. And so it's all CNN based. It's all CNN based. Then they have some problems they've been suffer from using CNN. So in 2018, we have new 2017 and 2018 we have new architecture we call ResonNet. Almost the same time. So this is the development of CNN. This is almost a development of CNN, and they try to solve the ResonNet. Try to solve the vanish of gradient. So the gradient is as important as you can imagine in no matter what optimization and backpropagations. So there is a problem that's a known problem for CNN that the gradient will no longer exist. Okay. So some people are trying to solve it, and then we have ResonNet. The ResonNet implies a skip connection. The very famous one is ResonNet 32. We've got an IES 32, IES 64, and IES 101. Got several different kinds of network. It's a name of network. And also we got a very famous name we call UNet. Okay. So typically, CNN is the most powerful and most common algorithm or network structure you can find in reality. So when you try to processing data with image like structured data with a tensor or a matrix, then CNN is somehow you can try first. The reason why is I will show you later, but that it's now the most promising and most useful, most applications in the world. So if you take a look at there is some parking lot in there's a gate right in the parking lot. So now they have the applied recognition system, so you can just drive there, and they will just recognize your plate license number, or plate number, and then you can just drive through the gate. The gate will rise up. So the system is also based on CNN, this kind of approach, and make it very high accuracy, more than 99%. So the first one we can imagine is anyone can use CNN to recognize instead of human, and we try to make machines like a robots who can see, who can observe. It's also based on CNN. So it's like your retina. So CNN is like a retina, and convolution is not a new thing. So let's talk about something before. Okay, in here I got you. I provide some historical things. So it's not a new thing. CNN is inspired by the neuroscientist Wiesel in 1962. So it's not a new thing. So in 1962, the people inspired by the biology, neuroscience, or especially for your retina, you can imagine something that is happening. And the idea, we got a receptive field. In Chinese, this is we call it 感知语. Sorry, I provide in traditional Chinese. This it's a receptive field. Okay, in 1980s, we got a recognition. It's multi-layer architecture of CNN. Okay. So the reason why it failed is they do not have the algorithm we call the backpropagation. And Yan LeCun in 1990s applied backpropagation to convolution network, and the first name is Learning-5. But if you like to train the model using CPU, then it's like a huge. I mean, five. This is only 5 layers. It's not 5 layers of the CNN. The whole structure is 5 layers. So it's a 5 layer deep neural network with the CNN layer inside. So it's the state of the art. It's the most powerful that you can find in 1998 because they don't have GPUs. They don't have like the distributed computing then. So the only thing you can use is CPU. Using CPU in this kind of a structure is very time consuming. So in 1998, I think most of you, I don't know if you have ever was born or not, but in 1998, the most powerful network you can find, the network you can find is .NET 5. So uh, so backpropagation is not easy. Nowadays, it's easy for you. You can even use your cell phone to run backpropagation. But back then, backpropagation need to run in the supercomputer. So that's why they only have a 5 layer structure. You cannot. It's really hard to imagine. CNN now you can increasing the layer to hundreds, several hundreds. That's easy, right? Now they can do thousands of CNNs now, but with GPU. Okay, so that's also another example of why the computing power, a powerful computation, is important in modern technology. So I think there is an important thing I like to say that you can also apply you can also apply deep neural network like DNN, MLP, multi-layer perceptron to processing the images like I showed you before. You can use like this to processing images, processing handwriting, the MNIST data set. But the problem is there will be huge number of parameters, especially this is a trainable parameter. It's not hyperparameters. It's trainable parameter you need to determine. So lots of unknown parameter you need to train. And so the weight will be more than 10,000. A layer of 10, each neuron will be like 1 trillion. 1 trillion weights. Okay, you need to find them. So even larger images like a 4Ks or 2Ks images, there will be intractable number. Well, we say intractable number, which means the number is too large to handle, too large to manipulate it, to be computed. So the large number does cause an explosion. We call it explosion in the number of parameters. So that's why I like to mention here. Why don't we use the deep neural network, the typical way, vanilla one with like a multi-layer perceptron to do so? Because the intractable number, remember the word we call it intractable number, which means the number is too large to handle. Okay. Now we have the intract now, so there is some problem. So the number is another thing. But what is the consequence when you like to train a lot of number of the parameters? It's the training process. Remember the training process? It's like there is in numerical method we have a time complexity. So it's not linearly. The growth of parameters is not linearly. So in neural network, usually it's like an n log n. So the complexity sometimes it's n log n. So when your parameter increase, the increasing rate is like n log n. So it will be dramatically increased when the parameter increased. So there were the so-called explosion in number of parameters, making the training slow and prone to overfitting because you have too many parameters, right? Too many parameters is really easy to overfitting. So, and the other thing is, I have to mention that is translational invariance. So that it appears in different positions of the images, there will be a very different training result. So like you put a cat, you think about that. If you put a cat in the middle, in the center of the images, and put it in the edge, then the result will be different. The parameter will be different when you try to use MLP. The reason is each pixel is independent. Remember what I say? That each pixel here is an independent input to your neural network if you try to use multi-layer perceptron. Okay, so each pixel counts. If no matter what, where is it? It's independent. But in CNN, the problem we like to solve is what is the hidden feature or what is the hidden pattern, especially the hidden pattern. How to find out the hidden pattern instead of the only the features input. Okay, so that's something. That's the other thing that we need to figure out. So CNN addresses both issues by introducing the idea. One is a sparse connectivity. This one is to try to deal with the translational invariance. This one is try to deal with the translational invariance. And weight sharing is the convolution kernels. We introduce a kernel. Kernel is a function. Okay, you think about kernel is a function, and this function turns out it's a matrix, and that's all. So usually when we do mathematics, you need to find out several different kernels, right? Before, like a Bessel function, like a Green's function, is also kernel. This kernel function is the way you can use as a basis to expand your function spaces. But in here, the kernel is a matrix, is a constant matrix. Remember that it's a constant matrix, but it's undetermined when initially. So you need to find out the best way to determine the constant inside each kernels. So I don't know if you guys are familiar with Photoshop. So Photoshop has a lot of filters, right? The filter is, you can think each filter is a kernel. So how to define a filter? They previously, Adobe Photoshop determined this filter by expert. So they have lots of experts working on computer science, working on image recognitions. They determine, okay, I need to put this kind of kernel with a certain combination of metrics inside. So that's before human determined kernel, human determined kernel filter. So you can think about this kind of people using like a beauty camera. The inside they have several different filters. It's all metrics. The metrics make you look better. The metrics make you look wider, and the metric make you the shape is better. The shape is much tidy, something like this. So it's all about transformation. We mapping your original raw images to a new field and using the linear translation, linear transformation with biometrics. So we apply by applying a kernel. So the before we do things like this, sorry, before we do things like this, we got the images. People doing things like this, we got the images. So this is an IMG. So it's, let's say it's 2084 times 1024. And then you process it, we apply a filter. So this filter is a matrix. So this filter is, it may be larger or maybe smaller, but it's no matter what, it's a filter. This filter can be a brush. You remember they get the tool called brush. You can brush through the shape of chins and your skin to make it look better. So the matrix, maybe it's A times A or it's 6 times 6, but it's determined by expert. This one is determined by expert. So how do they apply? The apply to this is, we call it a convolution. So in Lagrange or Fourier transform, you see that you got the Fourier or Laplace f star g is the integration of f and g of star, right? dot, and we do over the domain, something like this, right? You do something like this. So it's a moving. In this idea is it implies two things. One is multiple, and the other one is moving summation, right? You got integration over a domain, so it's a moving summation. So which implies two things. One is multiplication, and the other one is moving average or moving summation. So the idea is we apply the convolution here, we apply a convolution here, and next step, we apply the convolution by shifting it. And then we do the whole process with, and each one there, when we do the first one, we do multiplication. So in this domain, we'll have a new matrix here. We have the number of new matrix, and this one we got a new matrix, the number by multiplication. We got an A times B, AB matrix. Another one is also an AB matrix. So you got another one of the combination. So we collect all of them, and then that's all. So this is the idea of CNN. They're just moving the kernel, moving the function, and moving the matrix, also moving the matrix, and we do multiplication. So there is the A number, the A, which means the kernel, the CNN or the kernel. We say the kernel. Sorry. A is kernel matrix. It's undefined, so the initial number is guessed. For now, before it's human determined, right? Before it's human determined, but for now, you need to determine this parameter by machine. So through the training process. So it's guessed. Initially, it's guessed. And the B is the raw data. So the B is the input value in this domain. We think C kernel size. Okay? So you got the very important approaches from before. That's what we do with mathematics. So we do a lot of image processing or signal processing used the same way. No matter what, the Fourier transform or Laplace transformation. So you got everything is based on the kernel. We transfer things by integration, by applying integration. But now we made this integration easier by apply moving summation. Okay. So the goal of this is try to determine a filter or try to determine the kernel function by training or by pseudo data by training process. That's most important thing that you need to understand for CNN, and that's all. So in order to make things faster or make things better, so let's think about that. So in this domain, it's a limited domain or smaller domain. So we call it sparse connectivity because it's patch like a patch, moving one by one. So you can take a look of local region one by one. It's not a globally. You take it locally, right? So this is the nature of sparse connectivity that we say. What we say that we try to fix the translational invariance. So this one, why we apply CNN? Because it's a local patch. So you can see the local pattern instead of see the global pattern. So they can recognize local pattern or recognize pattern locally. So this is and the other one is the sharing. So remember what we call sharing, because you got the matrix plus that, so you got the real number, right? matrix application A times B, you got the real number by sharing this all information into the kernel, right? So all this information, maybe 4 times 4, 5 times 5, like we take a look at like 3 times 3, okay. We see this is a 3 times 3. So this 9 pixels sharing one parameter, right? 9 pixels not only sharing one parameters, and that's all. So you can reduce this kind of the size of parameter need to be trained or need to be processed by huge amount of the number that you can apply. So that's the kernel function or the CNN. It's important or easily to much more convenient to train or to achieve high performance in the like a structured data. We call it structured data. Is non-structured data is then it's not that easy use CNN, but structured data, what we call like images or pixel or voxel in the 3D, it's really easy to manipulate it or train by a CNN network. That's why. So when you apply this kind of an approach, they got a real number, right? So this real number can show you which one is better, which one's important, which one is it's applied to the overall predictions, make it perfect for recognition of the local patterns. So that's one thing. One is so let's go through it again. So the two things that the typical deep neural network cannot do is one is too many parameters, intractable number of parameters, and the other one is translational invariance, right? So we're dealing with this by applying CNN, but how? The CNN is they get the matrix times matrix, so the parameter being reduced for this local parameters only need a matrix instead of a 9 independent. And remember, this parameter is passing through the whole domain. The parameter is passing through the whole domain. So they need to find the best way to recognize all the patterns in the overall images, not just a single pattern. So that's why they can reduce the parameters. And the other one is because we apply it locally. So you can think about the locally is a receptive field by this, not just by the overall the whole input with the raw data. OK， 所以这边要特别强调一下啊，它怎么解决我们讲 CNN 的问题 ？CNN 是怎么解决传统在影像识别上的困难点？第一个是它其实利用了分散式的 weight 啊，就是你共享这个 weight， 它其实基本上一个 CNN 会扫过整张图片，并且它扫过去以后才会决定一个参数，整个 CNN 大小的参数。所以它其实你之前来讲，你整张图片1024乘1024，你就是至少要1024乘1024个参数嘛。现在我只要一个 CNN 的 kernel， 甚至是30几个 CNN 的 kernel， 我就可以做了。所以它的数字是降低的非常的快的啊，你的需要训练的参数是降低非常快的。第二件事情，它其实因为我就是 local 看嘛，我不是 global 一次去做判断，我是 local 去看它 pattern 的变化。所以它的问题是什么？它的训练起来，你每一次 neural network feed 我们讲 forward passing 的时间，用 CNN 跟传统比 ，CNN 一定会比较慢，这个是必然的。但是 CNN 的因为参数比较少，所以训练起来绝对比你传统的 deep neural network 来得快。哦，所以这就是为什么后来我们采用 CNN 去解决我刚刚讲 structured data， 就是说你一定是 n 乘 n 或是 n 乘 n 乘 n 这样子的 data， 它一定是逐例整合成这样的格式。那你说对文字来讲，它就不适用，为什么？文字它基本上没有个固定长度，没有个固定的结构嘛，哦，所以它的结构基本上是可以随着文法变化、随着语言变化的。所以对于文字处理，其实你就比较少会看到有人用 CNN 去处理文字啊。所以 text to image 或 image to text 其实基本上是两个不同的模型在做转换。好 ，so that's an important basic idea of CNN. I think we'll go through some mathematics later, but there will be a little bit involved. So I think we can take a 10 minutes break. Okay, let's get in back. So that's a lot of mathematics. So yeah, let's go through this. Okay, so the basic idea that you need to understand is, so the images usually we call it that's a different images, but usually the images contains like we can think about like a JPG, JPEG file, okay, or the TIFF file. So it contains several things. One is they got a RGB, 3 layers for color images. Okay, so they're gonna have RGBs, and some images will provide more information, like the coloring, saturations, and some other informations regarding this. Said where you take the photo, what is the machine, the camera used to take the photo. So the layers could be more, and the information could be much complicated than you like to process. But for now, we just think about RGB, and more easily, there will be black and white, the only single layer. We got only single layer, it's a BW layer, black and white. Okay, so usually it's like this. So you think about images, and there will be 3 layers, contains the same thing. So so you got the layer, we call it R, G, and B. Now each layer contains the information with red color and green color and black and a blue color, which we expected. So and each pixel contains the intensity of you think about there is a light, the combination of different lights, so the intensity is like the wave is excited in red or not. So the intensity is from 0 to 255. Usually it's from this domain. Okay. So in these images, you can find, okay, that's something that we need to think about. So in black and white, there's just only one layer. In black and white, there's only one layer, only single layer. So it depends on the size. So let's say the size is n times n. Okay, so that size is n times n. And then we got the kernel. We got a kernel. We use I. Oh, we use K. Sorry, let's use this is images. We call it I, and we got a kernel K. So K is like n times n. And remember that m is smaller than n. Okay. Usually it's much smaller than n. So they would do something like this. We got a product, like what I say, sorry, like what I say here, like what I said before. So we apply this K in here, and then you move K, you will move it to the next one. You move K here, You move your k here, and the mathematic way, the mathematic way we saw that it's summation with I images for x plus I and y plus I. So the xy is the coordinate of the pixel times k ij. Okay, the I and j is I is from 1 to m. J is also from 1 to m. Okay. So this is your output. So once you apply this, then single there, that there will be summation by a single number, right? Okay, so that's this equation. That's this equation means. And if you make it RGB, there will be 3 different kind of channels. You need to combine them together. Okay. The C means the channel. Okay. And but when you try to do the process, there will be something. That is one thing. The stride. The stride, which means the moving distance. How long would you like to move? Okay, so it's not necessary to be one. Okay, but usually people will use one, but sometimes we'll try to use convolution in different layer and in different way. Like a very important, very famous network we call WebNet. The WebNet is using the different stride number from 1, 2, 4, 8 with a different stride number. They try to processing with a longer coherence of your network. Okay, so it's not necessary to be one, but usually the stride number is one. So usually a stride of one. And when you try to apply 2, they will jump 2 pixels. So sometimes we just need to have a quick like a quick tuning that you can do 2. Okay, but it's you no longer it's not necessary to be one, but usually we'll try 1. Okay, the longest stride produce smaller output feature map. Okay, so if you have like too many parameters, you need to figure it out. You need to train, or maybe you can try with a larger stride number. But I think the GPU now it's not limited by this number, so it's not relevant to this. It's irrelevant to that. Okay, so let's try with the output number. The output number is you can see that if the input is h times like what we say 28 times 28, and the kernel size 3 times 2, 3 times 3. So you can think about now. Now your number is your output number. So after the feature map, the feature will be 28 minus 3. So if try is 1, then it will be 26, right? Then the feature map will become smaller. Okay. The reason why, because the size of a kernel, right? The size of a kernel, they can cover several different approaches. So the final one, you don't have to move to the final kernel. The final one is moving to this pixel, and then they can cover the whole images, right? Because the kernel got a size. So the reduced one because of the size. So you only need to move to here. You only need to move to here. So this is the reason why we minus k. This is the reason why we minus k here. It's because the only thing you need to move is here. But till k, you need to apply one more feature output, right? This one will still have one more output, so you need to plus 1. So this is a plus 1. And divided by the stride is I need to do how many times? So I need to do how many times? So if you do 1 by 1, then there's 26. If you make it 2, then there will be only 14. Okay? only 13, sorry, only 14. Yes, only 14. So sometimes we try to make the images and the feature map the same size. So you can do the padding. So the padding is like adding extra rows. So if you like to make the images, the moving size is the same, so you can make the images bigger. Right? You need to make the images bigger. So we usually do the padding. So the padding is to make some extra things outside the pixel. And then we added some number is irrelevant, maybe make -1 or 0 or sometimes. So it's mathematical. It's not mathematical, it's just numerical. You like to manipulating the feature output with the same size. So the padding is like this. Oh, so I think it's not relevant, but the relevant thing is receptive field and the feature maps. The receptive fields and the feature map is important. So a feature map, a feature map is something that processing by this. So after that, you will get the new feature, everything. We got this result, and then we put it in here, and then this result we put it in here. So you got a new feature map, right? So this is the feature map after applying CNN. Okay. And receptive field is defined by the kernel size. So what is the kernel size? So the receptive field is 3 by 3. Then this is your receptive field, the size of the receptive field. So if you like to enlarge your receptive field, how do? You make the kernel bigger, right? You make it from 3 times 3 to 5 times 5. So the thing is you need to figure it out. Do I need to change the filter, the size of filter? It depends on the feature map. So you need to take a look at the feature map. Is the feature map exactly the same with your original images? Then the receptive field is too large. You need to decrease it to make it better. Okay, so it depends on the feature map. Okay, good. So sometimes we will have a pooling level to for some reason. The most reason is try to solve the memories, try to save memories, and try to reduce the resolution. Sometimes you can do average pooling or max pooling. I will show you later. Okay, and there will be much more complicated using forward and backward propagations in convolution neural network. I just leave it here for your reference. We're not going to go through everything. It's a little bit involved. But let me show you the Learning-5. In CNN architectures, usually we got the Learning-5. It's by Yan LeCun. Okay, Yan LeCun is at NYU. And Yan LeCun this year, and I don't know why, but this year Yan LeCun is drawn by some very famous because he's the leading scientist in Meta. In Meta is Facebook. Facebook is the one that usually in the first beginning is the leading role in natural language processing. I think in 2014, 2017 they got a huge successful in Llama. But recently, once we got the OpenAI and DeepSeek, they got huge success in this domain. Llama become like obsolete. There's no reason because the people point fingers to LeCun because LeCun, you're refusing to embrace the transformer in several ways. Okay, so that's why. So they think about that LeCun. You should be the one to plan that the Meta now is not the best company in large language model. But LeCun is the author of not just Learning-5, also the handwriting data set, the MNES data set. He's the author of collecting all this handwriting data set. And LeCun is the professor in NYU and also the receive of 2024, 2022, I think 2022, the Turing Award. Okay. So he's like a godfather in CNN and in image recognitions and in deep learning. I got a chance to sit in his class in Harvard University. See, he been there for a lecturer to give a brief introduction of CNNs and energy methods in neural network. So it's crowded. He invited by the Harvard Mathematics, so it's crowded. You can see that more than 1,000 students inside the lecture just to sit in this lecture in his lecture to then how the masters think about CNNs. So this is the following content is directly from LeCun. And so I summarized them from my notes. So and LeCun make an explanation of how he invented the Learning-5 and what is the original idea of using Learning-5. So back then, there in 1998, let's go back to 1998. There's no iPhone then. The best, I think, the best mobile phone you can find is a Nokia, and there is less no like a supercomputing there is it's extremely slow. So in that situation, you can think about how they do with neural network is quite challenging here. So they expect a 32 times 32 grayscale. So it's an MNEST. It's usually like an MNEST. So the data set accompanied by this is 25 times 25. And so we got zero padding to make it 32 times 32. So the zero padding, what is zero padding? Zero padding, which means we supplementary with the extra pixels by zero. So you can see that all the zeros just surrounded your original 24 times 24. So the network composed of 7 layers. 7 layers, so you can Learning-5. So that will go through it layer by layer. So the first layer is a convolution layer. And the second layer is a pooling layer. And then we got another convolution layer, another pooling layer, and finally we got dense layer. We got several dense layers. So this is the typical way we got for the CNNs. Okay, we got a CNN applying for kernels, and then you got a feature map. So the C1 is kernel with 5 times 5. So that's why we make it 32 times 32, because the feature maps will be the same with the input size. Remember what I say? Okay. So each filter, they got 6 filters. Each filter has 25 weights and a bias. So the total parameters is this. But in before, how many parameters we need is 6 times 28 times 28, right? So in compared to this, you see the parameter using sharing parameters make the trainable parameters decrease dramatically. And then we got subsampling, the pooling. So pooling is a 2 by 2. We got 2 by 2. So each 2 by 2 there. So we got the feature map like 28 times 28. And then each 2 by 2 we do summation. Okay. So we do summations and do average. Or maybe you can do max pooling. Is try to find out the 2 by 2 there, and also it's not moving, it's by the next pixel to it. So the other one is from here, the other one is from here. It's not like CNN moving by single pixel, it's moving by kernel size. Okay. So if you do 3 times 3, then we got 3 here, and the other one is this 3. So we find the average value for each 3 times 3. Okay, or 2 times 2, like this. And then we apply another convolution layer. So it's also 5 times 5 filter with 16 convolution filter. And remember that, how to determine this one is 6 and this one is 16, and the kernel size and also the pooling size is we call the hyperparameter. It's a parameters you need to define. So you can try and error, try to find out which one is best, but you have no mathematical expression to tell you why this number is 16, why the previous layer is 6, okay? So it depends on that. And we apply another sample subsampling, and then finally a convolution layer. But before that convolution layer, before this convolution layer, we will do a flatten. We'll do a flatten. We'll do a flatten to make it a single array for them to put into the fully connected layer. Okay, and that's all. So they only have the 60,000 trainable parameters. Okay, so let's get to it. Let's do the Learning-5 in PyTorch. Okay, let's do it. Oh no. Okay. Okay, everyone, ready? So now we're going to use PyTorch to implement Learning-5. This is the first CNN network we can use now. Okay, but it's a little bit different. So try to follow up. Okay, so we got to import torch. This is a PyTorch and import torch .nn as nn, so you don't have to use nn again. And then we need to import torch. The functional as data sf. Let's import torch. Torch vision, the data set. So we need the MNET data sets as data set. And also we need to do some processing. So we'll have torch vision dot transformation. Transform as, okay. Now we also need something, we call it data loader, try to download data for you. So we can store it from torch ut utilities data import data loader. Okay, this, and then that's all we need for the initial module. So now we did. So everybody ready? So okay, need to make it. Okay, so let's define the structure of Learning-5. So Learning-5, you remember, you got the five different layers before, and then we got three connected, two fully connected layer, with also the final layer to determine, right? So let's do it. So now we need to determine Learning-5. Okay, let's do it. So let's create a class. Remember, for every neural network, you need to create a class, and this class need to inherit the under modulus. So the class name LaNet5 also inherits the under modular. So you don't have to create the neural network from the detail. They do it for you from this under modular. Okay. So let's define the constructor. So we need the constructor, the INIT with self. Okay, so remember what we do? We use the constructor from the parent class, right? So you use the keyword called super, and with your own class and the self, which would connect it from your parents, we call it INIT, use the constructor from them, and that's all. Now let's define the convolution layer. Convolution 1, we call the C1 layer. So C1 layer with the input. So what is the input size? The input size is the input size with single channel. With a single channel, what is the kernel? The number of kernel. Number of kernel is 6. And the kernel size is 5 times 5. So do you have any questions? Do you have any questions? Any questions? I keep hearing from you, so any questions? Okay. The kernel size. Kernel size is 5. So now let's do it. So remember the way we do with self, which means imply this is the instance. Inside the instance, the convolution 1, the first convolution there, is the unknown dot convolution to the COMV. To D. So the input channel is equals to 1, and the output channel is number of kernels. This is what we call also the output channel. Output channel. Output channel is 6, right? And the kernel size is 5. So this is first time we're using CNN, so I'll take it slowly, try to keep up, okay? I'll try to use tab. They will make your writing faster. We don't need to determine path pooling here. But pooling is a function. Okay, so we'll have you need to determine pooling in the forward, but not in here. Okay, so the other thing is we need to determine the other layer we call convolution layer C3, right? If you take remember to know we got a convolution C3 is also a convolution neural network. So we got now the conversation that let's go to C3 there. Remember between C1 and C3, there's a pooling, right? Subsampling 2. So we got a pooling inside, pooling in between C1 and C3. But now let's do convolution C3. For the input size, let's make it with input. The input channel, remember, is 16, right? Is 6, right? Also 6. Input channels is 6. And the output channel channels is 16. And the kernel size is also 5. Okay. So let's do this. So we got self COMV2, the second convolution layer. It's C3 there, but it's the second convolution layer. So we use COMV2. And then the COMV 2D. What is in channels? The in channels is 6, right? Remember? Now we got input channel is 6 because it's taking the input from the previous input channel, a previous CNN channel. So the input should be previous output. Okay, remember? Okay, so this is the idea. The input channel should be 6, and the output channel should be 16, right? Output channels is 16, and also the kernel size is 5. Okay, so use tab. So use tab is the thing you can make sure that you write everything is correct. If you hit the tab key and nothing shows for you to select, then there might be maybe some typos, some keyword wrongs, and some errors above your current statement. Okay, so just try to hit the tab key always. But make your writing faster, and also to figure out is there anything wrong with your writing, your coding. Okay, good. And then let's move to the C5 layer. We got the C5 layer. C5 layer. Okay, now tell me what is the input channel. So the input channel should be the previous output channel, right? So now, what is the previous input output channel for the C2? For the C3 is 16, right? So the input channel here is 16. And what is the output? The output channel is determined by you, so we like to make it 112, right? Output channel, because we need them to meet the size with the same size. With the same size of the, let's see here. Let's see here. It's in here. Right? C5 with here 125. Okay. Okay. That's all. So, what is the kernel size? The kernel size is also 5. It's also 5. Okay. So let's do it. The self, we got self convolution 3 is equal to NN the COMV 2D. Okay, we got in channels. We got in channels is 16, and the out channel 120. 120, this is a huge number. And the kernel size says it's also 5. Then we have to determine the fully connected layer. The fully connected layer. FC6. The sixth layer of this FC6. So the input is 120. The output is 84. So let's write it. So remember, I don't know if you remember what we do before. So it's FC1. The fully connected layer of FC1 is the NN dot linear, right? Remember what we use is the NN dot linear, and with the input feature. Sorry, in features is 120, and the out features is 84. The final layer is the input, the same, the input final layer FC7. It's also the output there. We got the input is 84, right? And they should be fitting. We fit the data from the previous layer to the consecutive layer. So we got this 84 inputs. And so think about that. This is the final layer, right? How many should we output? So the data set, that to remind you, the data set is a handwriting digits. So how many digits should we have? How many digits? We got the arithmetic alphabets from 0, 1, 2, 3 to 9, right? Only 10 possibilities. So the output should be 10, right? So ideally, they will show you which one belongs to which. So if it's the higher possibility of 7 or higher possibility of 8, then they should be have output located in this weighted, right? So the output should be your label size. The label is 10, so we put a 10 here. So we got self, the fully connected layer 2. We got NN, the also linear. And the in feature is 84. Right, the in feature is 84. 84. And the out features should be 10 because we got the 10, only 10 categories for this. Okay. And that's all. That's all for your constructor. We finally construct everything that you need in your. And remember, guys, this is only the first CNN that we have. Is very simple CNN. So if you can imagine if we move to the generative model or some very complicated CNN connections, the initialize will be very tedious. So you need to write it down everything before that, like what I show you for the Learning-5. You need to write down everything. What is the network structure you need, and how would you like to connect is determined by the next function we call forward. So you need to collect all the input output together first, and get everything ready for connected. So now we got every element we need and specified by the hyperparameters. So if you have any hyperparameters you need to determine, then you need to determine them in the constructor. Okay? So the filter size should be different, right? If the filter size, how many filters you need, and the size of kernel should be different, right? So you need to specify them. And also the dimension of a fully connected layer is also specified in this default constructor. So remember, if you like to create your own CNN, remember that every hyperparameters need to be determined inside the constructor. And then that's all. That's all for the first one. Let's move on to the forward. How the model is passing, how the model is connected. Okay, so let's talk about forward. Remember, this is the standard way we do with this. So we got forward, we got self and the x. X means the input. Okay, the input, which means x, also the flow. So the first layer. The first layer is passing the information. We passing the information to the convolution layer 1, right? So how do you pass it? You got a self for the convolution 1. Why we need this? COMV1. Why we need it? Why we need it? Why we need the COMV1? Because the COMV1 is specified by you. Self.comv1. Some people may write some comv1. It's not the one that you specify in here. So remember to tell them itself. It's inside this class. Use self to tell that this machine that it's inside this class. So I use self. If you do not remember, if you just forget it, then there will be some causing some problems. If someone writing a state name comv1 in global, then you will include this global function inside instead of your own convolution layer. Okay? So remember that I need my self convolution layer, right? And what is the input? Input is x. So I put the input x inside, right? Now that we feed the data into the convolution layer. And then remember what we do. Put them into the function, then what you need. In not just pushing them into a neural network, another important aspect is what? You remember? You just had a midterm, right? You put them into, you feed the data into the neural network, right? They got the weight times input and including the bias. Then you feed them into an activation function, right? Right? You need feed them into activation function. It's an important thing that we can introduce nonlinearity inside the neural network. So what is the activation function? You can try in CNN. You can try rerule. You can try hyperbolic. You can try sigmoid. And in here, let's try hyperbolic tangent. Okay, we haven't show you the hyperbolic tangent, so I will show you use hyperbolic tangent here. So the way to use hyperbolic tangent is easy. So now you need to feed them into hyperbolic tangent, right? So you need the function. This function is hyperbolic tangent. So you will not determine it by yourself. So we use, some people do it for you. Torch, they provide hyperbolic tangent, so you can use tanh here. Okay, now, so this is the whole process of feeding input into a CNN layer. Remember that lots of students forget they need an activation function. So they just show me the code. I don't know what's wrong with my code. My answer is always incorrect because they forgot to put this data into the activation function. Then the network is always linear. Okay? Only the nonlinearity appear in the activation function. And that's a way you can find the determinant, the gradient of your network. Okay? Otherwise, everything will be linear. So remember that. After that, this is your output for the first layer, right? And then there will be input for the next layer. Remember? Once they're passing through your layer, then there will be an input of the next layer. Right? So what do you express it? I remember, as I show you, x is the input, right? So x is the input. So we statement like this: x is now this. So that's the reason why I spend so much time live coding in the lecture, because I like to show you the rationale behind this statement. It's not just show you the statement I like to show you the logically, so you can improvise when you need a new thing. You need to revise the new network. You understand. Okay, this is logically like I can change it. This is something that I can do. If you like to deal with very complex connections, you need to think about which one is my input, and this input could be several from several locations, several different feeds, and a single feed can be several different branches. So you have this clear model in mind. You need to express them in the statement. Then this is the important thing that we do. It's not just for the coding. You need to understand why there's this statement like this. Okay, so the first one is. So any questions for this one? So let me show you again. So you need to decode it from the shell like an onion. So finally core is we put an X into a convolution layer. This layer is determined by me in the in the constructor here. And then we apply a hyperbolic tangent as an activation function. And this one will be stored as an input for the next layer. Okay, so this whole statement you can express like this. Okay, then let's do it for the next one. So what's the next one? The next one is max pooling, right? So we put a max pooling. The max pooling, this function is provided by the function node. So remember where do we have the function node? In the first beginning, we got a function node here. Function node as f, right? So it's a function node. It's not a function. It's a function of function. We call it function node. So the function node is max pooling for your feature. So how do you do it? We put this x into max pooling. So you can do f.max pool. Max pool 2D. Remember, it's 2D. Okay, max pool was 2D. And put where? Put good inside. Put your input, right? Put your x inside. And you need to determine what is the region to do the max pooling. I told you before we do 2 times 2, right? So you need to let them know the size is 2 times 2. So the kernel size is 2. And we'll do pooling side by side, not by moving, right? Side by side. So what is the stride? The stride should be crossing to the border of the other kernel, right? So the stride number should be what? Should be 2, right? So there will be, you can do the summation side by side like this. Let me show you. So this is the input feature 28 times 28, right? And we like to do max pooling, so we do the 2 times 2 max pooling. And we would not try, the thing we don't want to do is moving. We like to do the side by side. So we like the other one, the pooling from here. So what is a stride? The stride is moving 2 pixels, right? The strides need to moving by 2 pixels. So the stride is 2, okay? So if you do max pooling, you can determine it, but the reason why we do it is try to reduce the images, try to reduce the memory cost. Okay. So what we do? So the stride, STRIDE, the stride, ST. Okay. Then what we do? Is that correct or not? Is this correct or not? Something wrong, right? So remember after pooling, this one is your new input, right? So new input, which means X being updated by this. Okay, always remember that. Okay, let's do, so what's next? To put them into a new convolution layer, we call C3 layer, right? So we put this X into a C3 layer, so it's self.conv2, right? .conv2 with X. Okay, and again, we after put them after after passing through the neural network, what we do? After passing through the neural network, then you do torch the tangent, right? Hyperbolic tangent as an activation function. And then use X as this. Okay, again, let's do it again. Then you can copy this. We put them into this again. So that will be easy. Okay, so let's do it again. So we can just copy this, theorem B3, we put them into theorem B3, and that's all. So we're moving faster and faster. Now, we will need to do one thing that is important to before we can pass them into a feed-forward network. So this is an n-dimensional tensor. This is not the not the one-dimensional vector. This is a very complicated with a different channel, different layer, different filters. So it's filter by filter. Then we need to flatten them. So in this way, that we do flatten is to make the view in 1D array. So the way we do is flatten it. We call it X W. This is a tensor operation inside. So this is a tensor. So X dot size 0 is the row and column, the first one, the first how many rows we have, and the -1, which means backward, okay. And then we put them in here. So this is flattened. The flatten use the view. A view is the way we manipulating a tensor. So this is the way we can change it into a 1D array. Now you have the 1D array, you can put them into a fully connected layer, right? So now let's do X. So now we have the layer need to go to the fully connected layer. So we got a self.fc1 X, Y. And then remember what we need. After neural network, you always need an activation function, right? So you need a torch. Let's do hyperbolic tangent again. Tangent X is equal to this. And then finally, we got to fit the X into FC2. And for this one, do we need to put them into activation function for this one? We need the results for 10 different categories, right? So only 10 different categories. We need the number is reflect the probability. So no more activation function apply or nonlinear activation function apply. We only need the number. So it's a linear activation. So you don't need extra activation function after that. So let's just use X is equal to this. Then you can return X. That's all. Write a simple CNN. It's not as simple, but it's more logically. You need to understand how the flow is changing. Once we have the generative model, it will be more complicated. So I think this is very good time we can understand how it's doing. Okay. Okay, now let's try to do the data processing. So remember that what I say, what you need is we need this data from, initially the MNES data is 28 times 28, but we need them to be 32 times 32, right? So you need, we call it transformation. So you need to determine a transform. We need to determine something. It's an object called transform. It's collected of the several functions. We need to do the transformation, and then you can do the transforms from a functions collected from transform. We got a transforms is modulus. I remember we got here. Okay, we got a transforms. Then you can use compose. Compose is combination. Is the class the combination of lots of things. And remember, you need the list to input everything. Okay. So how many the things we need is we need transforms. We need transforms that resize. We need them to resize to 32 times 32. You need 32 times 32. And importantly, you need to make it to tensor. You need to make your data to the PyTorch tensor. Usually there will be a NumPy array, so we like to make them to a PyTorch tensor. So there will be a tensor data set in the container of data. So also you can do transformation, maybe the normalization. This normalization you can apply the standard deviations or in the mean value. So I just provide a number. Usually you need to compute this number by yourself. We just use it from paper. Then sometimes in your own data set you need to do it. Okay. Okay, now we have our transform ready. So why we need to determine the transform? Because when you loaded your data, I try to download your data, then this data loader will apply this transform directly to the model. Okay. So you can have your trend data set. The trend data set is from dataset. Dataset.mnest. Mnest is a class. You can apply the root to the current, sorry, you need to use this to a current folder using a dot. And then we call it data. The trend is true. True. Download is true. The download is true. Also the transform. Then we got a trend loader. We use data loader for trend data set. Trend data set. The batch size. The batch size, we need to determine the batch size. Use 60 for now. And shuffle is true. I will explain it. Okay. These two statements is usually the typical way, like ordinary we do, with data training, loading data sets. Okay, we use two things. One is determine the data set, the status of the data set, and where to download it. Is it download from internet using true? Do you want to apply for transform? Okay, then the trend loader is the way we fit the training data into your PyTorch network. So the data loader or trend loader is is an object help you to create an input flow. Okay, so this is two things. Data set is to determine where to find the data set, and the data loader is the real one work as a training process. Okay, and that's all. So if you do it, you will see something like this. They will download it from Yan LeCun. Okay. They will download lots of things. Okay. Oh, too many. And that's all. I think that's all. That's what we have. Anything? Okay. Good. Okay. Okay, I noticed some of you are using the computers with GPUs, right? So if you have GPU with your laptop, raise your hand. Let me know. Oh, good. So you can use this statement. So if you have GPUs inside, then you can determine the device. The device is torch the device. The torch will determine some device. This device, if it's CUDA, then you need to write a statement if torch dot CUDA CUDA is available here. Okay, it's a function. Else, using CPU, the CUDA, which means the NVIDIA GPUs defaultly. So they will find out if you have CUDA embedded in your systems and CUDA been installed properly, then they will use CUDA version. Then if it's not, they will use CPU version. Remember that it's not CPU, the device should be CUDA because it's specifically for the NVIDIA GPUs, okay? So if you have this, you can use your GPU to run, to train your process, that will be faster. Okay? So now, you got everything ready. Now let's instant your model. So your model is Learning-5, right? Then remember use two device. So you got your device ready, right? You got everything ready. Now what do we need? The two things you haven't specified, right? One is what? You passing your data into a neural network. After that, they got something that predict from the neural network. We need something to determine is this good or bad, right? This is we so-called the loss function. So you need to determine the loss function. And then after the loss function, what we need to find out how to update the data is an optimization process So we need to optimize it, right? We need two more things for a neural network. So the first thing is the criterion and also the loss function criterion here is we use this is a category problem. So usually we'll do with and then the cross entropy loss. Okay. The criterion usually for the categorical problem we'll use the cross entropy. And we got the optimizers using torch. Torch, optimize. Here we got the SGD, stochastic gradient descent. Okay, just to show you some that its model. What to optimize is your parameters. And the learning rate, determine the learning rate. LR is let's try 0.01. We don't want it to run too long, run for too many times. Okay. Okay, now you got everything ready. Then you need to write a loop to train your feeding your data into the model, right? The training set, the training process, how many epochs you like to do. Okay, so let's only do one epoch. You can do several different epochs. Let's only do one epoch just for demo because we are running out of time. Okay, so we got now we got model the trend. For epoch. We only do one, okay, because this is gonna take in CPU it's gonna take a long time. So we only do 1 to 2, so only one epoch. So let's do only one epoch. So you can change it. You can change the number. Only one epoch. Only one. Okay. So we like to processing the data. So you will have images and labels, right? Remember, in train loader. In train loader. So if you're using GPU, remember this is important part to do. Images, image, labels is equal to images dot to device. And it's important if you forget it, I forgot to use it, you're still using CPU, okay? To device and labels the to device. Then you do optimization, right? LPTI, optimizer dot zero grade to initialize your gradient, right? And the output is your models. We're feeding images inside. So we're feeding images into the data, then you can have it here. The loss function is criterion. The criterion outputs. The output is from your model, and the labels is from the data, right? And then we do backpropagation. We do loss the backward. Then we do optimization the step. That's all. Then you can print drops down. Okay. Oh, something went wrong. What happened? FC, which one is wrong? Ah. Two. Which one? Argument input. Position one. Well, let's see. We do have two tensors, right? Two tensor. Right? So outputs is models the images. Forward FC2. Oh, let me see. Tang FC1X. Okay. Something went wrong with this. 所以他帮忙看一下，你们之前有检查，可是我们之前有跑过吗？对，为什么会出问题？到底是哪一边出问题？啊？我打错字了，是不是？这里。在下面。这个。哦，对，打错字了，难怪我想说奇怪，为什么？谢谢。好了，来，应该在圈了啊 ，good， 谢谢。这同学你是哪一位？记一下，感谢。OK， 好了 ，then job start. Okay, so you can do prediction. We'll have more explanations and how the CNN is working next lectures. Okay, so this lecture is show you what the CNN is working. You can make them train more and to show you the laws and everything, and like what we do before. Okay, good. I think that's all for today.